The limit as x tends towards a of f of x is k. The limit as x tends towards a of g of x is L. Now L is not 0 here. So we are going to show that the limit as x tends towards a of f of x divided by g of x, in other words the limit of a quotient, is the quotient of the limits. Now the way we're going to prove this is to first consider the limit as x tends towards a of 1 over g of x. We're going to show that this limit is 1 over L, where L is the limit as x tends towards a of g of x. Now to prove this limit, we are going to have to consider the distance between 1 over g of x and 1 over L. So we can combine these two fractions together, get a common denominator of g of x times L. The magnitude of a quotient is the quotient of the magnitudes, so we get the magnitude of L minus g of x. Well, that's actually the same as the magnitude of g of x minus L. G of x minus L is just got by minusing L minus g of x, and when we get the magnitude of a negative quantity, it doesn't change anything. Then we have the magnitude of the product here in the denominator. Now we are going to look carefully at these three quantities. So to prove this limit, we pick our epsilon from the outset. It's any positive number greater than 0. The proof will make sense actually when I get to the very end and just work backwards briefly, but to make the thing work out we have to take a few convoluted steps. Now the limit as x tends towards a of g of x equals L. So that means that given some epsilon, not this one here, we won't use this for a while. So let's call this epsilon 1, and we're going to set it equal to the magnitude of L over 2. This will all make sense at the end. There exists a positive number delta 1 such that whenever x is within distance delta 1 of a, but x is not equal to a, then g of x is within distance of magnitude L over 2 of L. Now we can write the magnitude of L like this. I've just added 0 to L. Then we can apply the triangle inequality. And note that the magnitude of L minus g of x is the same as the magnitude of g of x minus L. G of x minus L is just got by minusing L minus g of x. And when we take the magnitude of minus 1 times a quantity, we just get the magnitude of that quantity. But when x is within a distance delta 1 of a and x is not equal to a, then the magnitude of g of x minus L is less than the magnitude of L over 2. So this thing becomes, this quantity is less than the magnitude of L over 2 plus the magnitude of g of x. So the magnitude of L is less than the magnitude of L over 2 plus the magnitude of g of x. Now we can subtract L over 2 from both sides of this inequality. The magnitude of L minus the magnitude of L over 2 is the magnitude of L over 2. And that's going to be less than the magnitude of g of x. So I've just subtracted this positive quantity from both sides of the inequality, and we can turn both sides of this inequality upside down to get 1 over the magnitude of g of x is less than 2 over the magnitude of L. And we saw earlier that when we're looking at the magnitude of 1 over g of x minus 1 over L, the quantity 1 over the magnitude of g of x appears. Now let's work with this limit again. This time we choose a different epsilon, which I will call epsilon 2. It's the magnitude of L squared divided by 2 times epsilon, where epsilon is the epsilon we chose from the outset. Now for this choice of epsilon, there exists a delta 2 greater than 0, such that whenever x is within distance delta 2 of a, but x is not equal to a, then g of x is within distance epsilon 2 of L. So for epsilon 2 I'll write in the magnitude of L squared over 2 times epsilon. Now we're going to put everything together. Let delta be the minimum of delta 1 and delta 2. Now let's get back to the magnitude of 1 over g of x minus 1 over L, which we briefly saw at the start. Well, we saw that that can be written like this. We also saw that it can be written like this, just using the property of magnitude of products and quotient, and using the fact that the magnitude of minus 1 times a quantity is just the magnitude of that quantity. Since delta is the minimum of delta 1 and delta 2, it is obvious that delta is less than or equal to delta 1. In other words, x is within distance delta 1 of a, and x is not equal to a. We saw up here that if that's the case, then 1 over the magnitude of g of x is less than 2 over L. So this quantity here, 1 over the magnitude of x, is less than 2 over the magnitude of L. Now, since delta is the minimum of delta 1 and delta 2, it is obvious that delta is less than or equal to delta 2. So in other words, x is within distance delta 2 of a, but x is not equal to a. And we saw for that situation over here that the magnitude of g of x minus the minus L is less than the magnitude of L squared over 2 times epsilon. But all of this cancels down to epsilon. So everything is contrived so that when we choose our epsilon from the outset, we can find a positive number delta. Delta is greater than 0 because it's the minimum of 2 positive numbers that are greater than 0, such that 1 over the magnitude of 1 over g of x minus the magnitude of 1 over L is less than epsilon whenever x is within distance delta of a and x is not equal to a. So to reiterate again, given any epsilon greater than 0, that's what we chose from the outset at the very start. Up here we didn't use it right away, but we actually used it down here when we were creating this other epsilon, epsilon 2. There exists a positive number delta, which actually was the minimum of 2 other deltas, but such a delta exists such that whenever x is within delta of a but x is not equal to a, then 1 over g of x minus 1 over L, well, the magnitude of it is less than epsilon. So that proves that the limit as x tends towards a of 1 over g of x equals 1 over L. Now the last part of the proof is straightforward because we can write this limit in this way. We can write it as the limit as x tends towards a of f of x times 1 over g of x, and then we can use the result of a previous video which says that the limit of a product of functions is the product of the limits of those functions.